Okay, now let me start again with the lecture of today, in which I will reconsider very shortly some aspects of last time, because I know that how possible to say is not an easy concept, the concept of the delta von Dirac, but not only. Also the concept of step in general. Let me say the impulse answer, the step answer. We have seen last time with some exercises which I will upload in my study exactly today, together with the last let me say example which I would like to consider today. Let me reconsider again this slide here, and then after doing this exercise to complete the analysis of last time, we will restart from the first slide in which we will consider the Laplace transformation. Last time I told you a little bit about this again, but because you remember we started directly from here, but I stopped basically here. Let me now reconsider in order to do an exercise this slide here, in which we can see, I don't know if I share, probably yes, in which we can see the definition of the delta impulse, no? Or Dirac impulse, or in some books, unit impulse. The definition is here. Basically, the definition consists of two parts, in which the delta of t, as this function, equals plus infinite if t equals 0, 0 if t not 0, and together with this part here. Basically is a repetition of let me say of this second part of this two sentences. We have this expression here, which defines somehow the function at 0. If I use here the word defined, is a little bit strange, because plus infinite is something which is undefined. Defined in Latin means limit. But of course, please pay attention, the words in this context is limiting. I mean, I can understand that at point 0 is extremely large, but I cannot understand what is the meaning of infinite. As human, we cannot understand infinite, and we cannot understand infinite small. Exactly here, this is extremely abstract, this sentence here, because at t equals 0 means, now we clarify a little bit better in a practical sense. But in one point, if the function is infinite, really it's just in a way to say, conceptually, it does not mean anything. Let me think abstractly that in one point is very large. We will see now with a practical example what we can understand with this sentence. Therefore, in math, we use the concept of limits instead of to say infinite, with something is going to infinite, no? In something which is going to 0. But what 0 is really difficult to understand. But anyway, let me speak abstractly. And this is clear, nevertheless. This is clear because it's 0 if t is not 0. Except for 0, this is 0. Here, I repeat it here. Very important, nevertheless, this part, because this is more understandable somehow. Because we say that the integral of this function between minus infinite plus infinite is 1. If you think about the concept of the integral from high school, if you remember, in high school we learned directly that is the surface between the function and the x-axis. Okay, we fix something more concrete, because 1 is 1. I mean, if I say 0 is already more abstract than 1. if I say infinite, it's really ununderstandable. Very important. Also, zero is extremely abstract as a concept. In fact, zero is an Hindu number. You know Hindu? The Arabic people, the Arabic system took this concept from Hindu. In Roman numeration or system, we don't have zero. We don't have zero. The concept of zero is the Roman system is not there because the Roman was practical people. No? That they don't. I mean, zero is really an extremely abstract concept. But let me go ahead. I will reconsider this concept here in a few minutes. Let me now try to understand the concept again using a practical example. Look, we have here three possible inputs, unit impulse or Dirac impulse. I would like in this case use unit impulse, but it's not wrong to say Dirac impulse in the sense of practical, in the sense of something which I can really realize also with Simul in MATLAB in any kind of software. Why that? Because as I told you, zero for us, it's extremely abstract. This means you can see that from here to here to here, I try to tend to zero, but in all these three cases, I realize exactly this part of the definition, which is, I would like to say, the most important part. The most important part because allows me to say, or allows me to realize practically this. Also in Simul in MATLAB, it's a shame I don't have time in this course to do an example and a practical. I don't know. It could be that I have a time at the end of the course to do this practical example. But we realize also in a paper after inside in a project, we're using the concept of delta. But let me go ahead. As I told you, if the concept of zero is in this context in particular extremely abstract, more abstract is the infinite, look how I realize a little bit practically three possible Dirac impulse or the practical Dirac impulse in which from here to here to here, we can see that we'll tend to this, let me say, part of the definition, but all three but it doesn't matter. Three impulse have this guarantees because this is the most important. The energy, let me say, or the power, it depends of the unit of delta. It depends of the unit of delta. Look, is the surface one? Yes, because this length around zero is 1. Multiply 1 is 1. This means this part of the definition is guaranteed. Of course, this here, plus infinite, is not possible to realize. No? What is the meaning? I don't have place also in my slide to realize plus infinite, but also for our way to think, plus infinite is just a way to say what is the meaning. Plus infinite means I can think of something large, but of course I can think that there is also something larger, and this is our infinite larger and larger. But around zero, somehow we can see that from here to here, we tend to define my impulse around zero. We can see that this is increasing. From here to here to here to here, we will increase. But in any case, all these three surfaces are equal 1. Look, from here to here, we have, what is the length of this? 2 divided 6. This means 1 divided 3. This length is 1 divided 3. Multiply 3 is 1. You can consider also this. No? Here, this length is 1 divided 10. Multiply 10 is 1. This means using this graphical representation, we can understand what I intend in sense of limit with this definition. But of course, I am not able to represent this. We will see how we will represent practically. But of course, no meaning in sense of plus infinite. Means larger, larger, larger. Okay, intuitively. Now, look at this. This is also another important signal in dynamical systems. In fact, last time we did an exercise concerning the step answer. We will see later. Here we have the delta answer. Delta answer. Where is this? Yeah, here we have the sigma or step answer, which we have seen last time practically in answer or the response, no? in the practical example. Let me insist a little bit on this because this signal here is relatively good related with delta. We can understand better this because first of all can be represented. We can see that less than 0 is 0 for t less than 0. For t larger or equal 0 is 1. That's the step. Do you remember I told you this can be used to model the switch? I don't know if you remember this. When I start to control a system, I use now the concept of the word control. When I start to monitor a system, when I start to analyze the system. Before this time, everything, at least we don't have somehow inputs. Look a little bit at this. I already told you about this possible representation through matrix A, B, C, D. Do you remember this at the beginning of the semester? I will come back on this. Now, look at this definition. And in particular, look at the relation between delta, which I already introduced last time, and I repeat it today, and sigma. You can consider both of this. Last time I insisted on this. You can look in YouTube. You can consider this expression here or in equivalent form, this expression here. Because if you do the derivative of this expression, we'll obtain this one. Because how possible to say you have to calculate basically the derivative of this expression here, which is delta of t equals the derivative of this. Because you cancel, let me say, the integral. Yeah. We will use exactly this. Exactly now to go a little bit more in depth. Yeah, on the concept of delta, considering this expression here. Look, again the example as before. Again the example before. Look at this impulse, real impulse. You can see that in this interval of time, I will change from this point to this point. This means we can calculate, let me say, the derivative, which is this distance divided this distance. The derivative, you remember, at least in this case, can be calculated in this form. What is the change over time of this, let me say, signal? And this is 1. Because inside an interval of 1, I change of 1. Clear. But also here, the derivative is 1. Because inside in the time, which is 1 divided 3, I will change 3. I mean, here it's clear it's 1. Huh? Yeah, why that is a little bit confusing, but I clarified the meaning. Again, here we change, let me say, from here to here, the changes is 1. Did you agree? But this change happens inside an interval 1. This means we learned in gymnasium, no? This distance, let me say, this distance divided, this is the change. What is the changes here? It's the same. It's again 1. Why that? Because, of course, we changed 3 from here to here. But this happens in 1 divided 3.
that represents the change, right? And the value only goes up 1. If we divide 1 by 1/3, it's 1. Right? The second example, the change of the Steigung ist ja nicht 1.
Let me think. Understand what I intend. Ja.
Dann der Step ist immer auf 1, egal was. Und in der anderen Zeit halt, jetzt zum Beispiel in einer Zeit, keine Ahnung, sagen wir die Kunden nicht in einer Sekunde, beim ersten Beispiel, sondern bei 1/3. Aber es gibt trotzdem noch 1. Die Steigerung ist dann immer noch äquivalent zu dem Wechselgrad von der D.
Let me think. The question is correct. Basically I copy from a book. Let me think how I can answer. Let me see. I think we can interpret it in this form. Think about this red function, which is a practical, more practical expression of this. This is also a little bit abstract because in an infinite small time, I will change in finite difference. Also, this is not so exactly. Now, let me interpret what I copy from a book. I have to say the true in any case, but of course, it's not my invention. The derivative of this is 3. Did you agree? Because 1 divided 3 is 3. Look, again, the red. No? Look at the red. The changes here of the red. Think of the red, not the blue. Probably I expressed wrongly at the beginning. It could be if you focalize the action, the attention here and here, but in terms of red. Why that? Because probably now I remember the book. But please pay attention. Here, you can read any equation in this form. Read this sentence here. Delta equals the derivative of this. This means you can interpret this is the effect of the derivative of delta. Math is we use words. Delta equals, or is a little bit more abstract, equals the derivative of sigma. Now, delta is the effect of the derivative of the sigma. Now, if you consider this sigma here and this sigma here, we can understand exactly that the derivative of this red, probably is better so to explain, is 1. The derivative of this red here is again 1. Excuse me, yeah, is again 1. It's 3, excuse me. Because I read here. Here the derivative is 1 as we want. And we want, why not? And here the derivative is 3. But you can see that, again, this is a unit step and a real unit step. More real let me say it on this one, because this concept here is again abstract, extremely abstract, because in an infinite small time, we will change from 0 to 1 in infinite small time. And here I didn't put, but you can understand very easy that if I put an, let me say, step from this point to this point, we change 1, the derivative of this is 20. This is a little bit the interpretation. Excuse me if at the beginning I don't clarify well or I made mistakes in the explanation. But because we are speaking about here, we are speaking about the sigma, the subject. It's sigma. The cause, it's sigma. We can see here, we have this cause through this transformation. I have this effect. Can be the equation makes sense if you read in this sense. The cause is sigma. Through this transformation, I have the effect delta. This means this graphical possible interpretation in practical sense can be interpreted looking for or focus on sigma of this red in accordance to what is written here. We will obtain the effect of delta. This example, so this explanation, I hope, together with this abstract definition, together with this previous introduction, after there is this abstract definition, I would like to say allows to clarify a little bit the concept of delta, extremely abstract, the concept of sigma, not so abstract the delta, but nevertheless not so easy to be understood. Okay, let me now switch on the lateral camera and let me reconsider a little bit what we did the last time. And I would like to propose an exercise connected with this, and then we will go ahead with the Laplace. Okay, let me now. Yeah, let me take some material. Last time, I would like to say in depth, or no, I hope that I have this material. Oh, I have it. 1 second. Last time, I don't have time to repeat because we did a lot of things together. No? But you remember, we analyzed this at the beginning, and I introduced the concept of sigma considering the switch. And I think we can reconsider an easier example at the end, because I would like to, yeah. This was the original example 2 weeks ago. That is not necessary to start from here. Let me see if I find, no? Okay. It is better to consider this because it's exactly what I do, what I would like to do. Do you remember this concept here last time, in which I told you that, to be more precise, I told you, even though here we can see that this concept of sigma is related to the system with the switch, in which I am considering here 12, and sigma, we can see here, UN is included this tricky situation. In one case, the free answer, in another case, the forced answer. But very important to remember that sigma try to model the switch system. We can see here 0 multiply sigma if I close in this position here in accordance with the free answer. But if I close in S = 1, we have 12, which U is 12. multiply sigma, which state exactly what happens when I close the switch. Now, what at the end we calculated was, and then we will go ahead with an exercise. Was a free answer as a fourth answer, and UC, which I would like to consider at the end, is the sum of the free and fourth, because we are in the case of a linear system, in the sense in which we can consider the sum of both. Now let me copy again this expression, and let me formulate a new possible exercise. Yeah, here before 0 was 5, and after 0 was this expression. We discussed a lot about that. If you want, I can remark also here, you remember the concept we discussed a lot. We will consider again this. No? UC at time 0 minus equals UC at time 0 plus. This means between 0 minus and 0 plus, we have the, let me say, the continuity of the function. We don't have any spring. This I will insist in the future also again. No? We introduced the concept last time, using in an easy example in which this was not guaranteed. You remember this? Let me show you in order to show what I intend, if I'm able to find this. No, it's not this. Now, where is? 1 second. I'm looking for the material which I don't find. Yeah. In this kind of system is not exactly the same. Do you remember we demonstrated that between 0 minus and 0 plus, look, and I will upload in my study again, I will upload in my study, we have the discontinuity. This means it's not always guarantees that what is a 0 minus equals 0 plus. In this case, for the voltage, it is. We demonstrated. But if you remember, it's not the same for the current, because the current is the derivative of this function here multiplied by C. And you remember, we discussed that between 0 minus and this 0 plus, the current is not a continuous function. But this voltage, yes. Now, we say that for the state U, the voltage, is continuous. For the current, no. Now, let me copy again this expression. And then let me formulate another exercise. In my opinion, extremely interesting exercise. 1 second, because yeah, I am so confused with this material, because I need to organize a little bit better. Otherwise, where is it? I had a block, which I don't see now. I found. The problem is sometimes I lose all material. Okay, let me copy this. Could be that I need material. Let me copy the expression, and then I formulate. Look at this. You see. Let me copy. This is a problem. I don't remember now. Okay. let me copy for you again this expression in the new slide, so we can analyze a new question connected with the delta. UC, as I told you, is UC3 plus UC fourths. This we discussed last time. No? You remember this was UC3, and this expression here was UC fourths. I can write also this. Now, let me analyze, or let me formulate another interesting problem. In order to introduce the impulse answer, I mean, this is the step answer, because everything was calculated, or at least the input was in sigma. Let me say here step answer. Let me say comment here. So with the example, we introduce already the concept of step response or answer. It doesn't matter. Now, let me consider now what happens in such a situation. In which I would like to analyze this kind of the system is the same. As before. But what we want to analyze now is what happens is if here I have a delta. And question is, what happens? Here is a possible representation in order to understand. In case we want to analyze, let me say, an impulse answer. Exactly. Let me see. This here. Let me switch quickly. We have a system. Let me switch quickly for. We want to analyze in concrete form exactly what I put it here. Answer or response is the same. You can use both. We have a system which is somehow concrete. Now concrete, I mean, is an exercise in our case. We already analyzed, where is this here? We already analyzed this here. The initial condition could be 0, could be, it doesn't matter what. In our case, it's 5. No, in any case, it's given. Here, we are able to at least, we did just an exercise, but we are able to understand what we intend with this concept here. Of course, I didn't use here the matrix A, the matrix B, the matrix C, the matrix D, because in case of system of just one state, the matrix A is exactly in a scalar, the matrix B is exactly in a scalar. Which one? I show you what is. We don't speak about matrices because we have just one state. In this example, I show you what I intend. What's this? Put here before the What is? Okay. The matrix A is the scalars minus 1. You remember, x derivative equals A multiply x plus B multiply U. Yeah, the matrix A is the scalars minus 1. If you think about the expression of the standard expression, x derivative equals A multiply x plus B multiply U. A, if you consider this element on the other part, this is our x, is minus 1. What is B? In order to consider B, we have to analyze the fourth answer. Where is that? The fourth answer? Yeah. Yeah. You can see from the first answer, you can see from here better. Yeah. If this is the input, you can see here, the B element is 1, again 1. I mean, B is 1, A is minus 1, as I told you. Therefore, in the system with one variable, with one state, we don't use the matrix A, B, C, and D. We will come back on this in the next lecture. Okay, let me now analyze or try to answer this question. There is a different, let me say, way to proceed in this case. But think about this concept. Let me say analysis, no? Or analysis. Think about that delta, if, let me say, if delta of t is equal the derivative of sigma of t with respect to the time. We analyzed this already with some examples. We can consider, see, this is a definition. It's in a definition. Why is it a definition? Because do you remember the integral of delta between minus infinity plus infinity is 1. This means this expression here reflects exactly. Remember, let me switch on again so we can understand again better without writing everything. It's here. This is the most important concept of delta. The integral is 1. This is equal. Of course, is consequence because before 0 it's 0, and also this one before 0 it's 0. And then we can consider in the same way we can these two equations are equivalent in the sense. If you do the derivative of this, do you remember math? We have this one. Now, assuming that this is what we know about these two functions. The question is, I have this now as an answer, and I want to analyze what happens. I have this as an answer if sigma is our input. Now, the question is, what happens if instead of sigma, I have a delta in the same system? What happens in output? The question is, can be understood in this sense. What is, in this case, U of C? Just schematically, no? Just probably this can be better understood here. Which the system is the same. The system. This is our, just to understand. Okay. Now, one way to proceed, I would like to say very quickly, even though somehow must be demonstrated, but the demonstration I would like to skip, but I would like to to explain, and I would like to explain in this form. Look at this idea. We have how possible to characterize this? Let me see. You see Pedix delta. But here we have UC Pedix sigma, and then we have. This means when can I think that UC delta is the derivative of this? Let me write this sentence here. And the answer is relatively easy. I can demonstrate later using the Laplace transform. It could be useful. It could be easy to be understood. This is always valid, and I write to fix. No? When the system is in a linear system. This means, let me write what I intend to explain. We have a UCC, comma, which is the answer, or let me see, without comma. Of the system. I would like to be more precise, of the linear system. It's not wrong what I say, but now is importantly. With respect to input sigma. Again, in case a linear system is our case, no? We can demonstrate. I will come back with the Laplace, no? Demonstrate that, please pay attention. The derivative of UC sigma with respect to the time, this is C, equals U of C delta. Let me write a little bit better. Sigma. Sometimes sigma seems to be in the delta, no? Is in delta. Basically, in order to understand better this, I would like to say, demonstrate that this one, because, let me say so, in a linear system, no, very important, this must be underlined. Because delta, or better to say, the derivative of sigma of t with respect to the time equals delta. Is intuitive. Is intuitive. What is intuitive? Delta is the derivative of sigma. If the system is linear, this is in the linear system, I introduced at the beginning what a linear system is, you remember. This is as if the derivative in input, again, this function is the derivative of this function here, migrates in output. This means this output here is the derivative of this. It's as if this derivative is migrates through the system, and to calculate this output is enough to calculate the derivative of this. It's intuitive, no? Because but please pay attention. It is valid just for the system is linear.
linear is on then. It's not
Yeah, it is intuitively because you remember the concept of the linearity somehow recall as the distributivity. Distributive means that an operator is passing through all elements of the of the element which realize in a linear system. Probably you have a better explanation than mine intuitively. Why you understood intuitively that makes sense if the system is linear, that if this function is the derivative of this, then this function is the derivative of this. Just intuitively, even though it's not a demonstration, but think if it's linear, the system. Otherwise, no. Why you intuitively understood this, or you have a feeling that we can trust this sentence in your feeling?
same kind of linear. Like just, I don't know how to explain it.
Yeah, it's with the feeling it's difficult to explain. Therefore, I'm asking you if you have a better feeling than mine, because the demonstration I will insist in the Laplace in this sense here. In time is, I don't remember. It's a little bit more complicated. Exactly to demonstrate. It's not. I have to look. I don't remember because I don't use it every day. Let me calculate it. That probably we can understand better in this particular case. Okay, this is the UC in case of sigma as an input. Let me enumerate with number 1 of the lecture today. Let me write this a little bit in this form here. UC of t. Let me sum up this and this. No? This means minus 7. Yeah. This means 12 sigma of t minus 7 exponent up to minus t sigma of t, right? Yeah, makes sense. No? Definitive. I think. This means here basically in time we didn't sum up at the end of the lecture because I didn't complete the calculation, but it's easy, no? I mean, here we have 5 until 0 minus, do you remember? But at 0 plus again is 5, and I will achieve 7. It's a little bit strange here. Let me take a little bit more place. Now a little bit better. No? This is the U which we calculated last time. 0 minus, 0 plus. And we analyzed that in this particular case, in this case, the state is continuous. This means no difference between UC at time 0 minus and UC at time 0 plus. This means continuous function. Now, let me do the derivative of this in accordance with what I told you today without an explicit demonstration in time. Now, let me do the derivative. The derivative of this. This we called, do you remember? This, let me use the notation sigma. Here, it seems to be in accord with what I told you, UC of delta, no? Respect to delta, assuming this notation here. Now, derivative of this. In accordance with the definition, just the definition. Please pay attention here now. The derivative of this, in accordance with what we learned in our math lecture. This is the derivative with respect to sigma. And then I have to consider the derivative with respect to this function. It's a product between exponent and sigma. Sigma is a function. This means plus 7 multiply exponent up to minus t multiply sigma. Do you agree? Did you agree with this one? No? Again, the derivative of this is clear. The derivative of this is clear. So this is a product between a constant and the sigma. But I write directly this because the derivative with respect to 12 is 0. Now, let me consider Let me consider the derivative of this product here. Yes, again a product, but the derivative of this is clear. Is it enough to do the derivative with respect to this one because the derivative of respect to this is 0. You remember the derivative of the product of two functions is the sum of. This means the derivative of this is the derivative of, for instance, of this function multiply this part without differentiation. This means sigma becomes delta, and this does not change. Okay, yeah, in fact, at the beginning, I told you sometimes it's not so easy in my calligraphy to recognize delta with respect to sigma. Right? Now, we have 2 times, let me say 2 times delta here and here, and you have a sigma. Now, let me go ahead. This means you see delta, excuse me, is equal. Look here now. What I can sum up here in European? What I cannot sum up? Alex. These 2 elements I can sum up. Why that? No, it's practically. Yeah, here more for dynamical systems. This means with respect to math, is a little bit more practical. Dynamic, we have to describe what would change. This is a little bit practical. Therefore, system theory, control is no practical. Look here. Why I can sum up this? Because at time 0, this is one exponential function. This means that these 2 functions, even though formally it seems to be different, it's the same. Think 1 second. How I can represent this? And let me write the result and then we discuss. The result of the sum of these 2 elements is 5 delta. Or if you don't like here, in this form, I can write 5 exponential function up to, it doesn't matter what, in this case, exponential up to minus t, multiply delta. It's the same. Now I do a comment for you. Let me do the result and then we will comment. Plus this not change. Multiply sigma. Sigma delta, it's the same. Why this? And now I try to clarify. Because, remark, let me say remark. Twelve delta of t is equals 12 exponent up to minus t multiply delta. Or, if you want, sigma is 7, excuse me, exponent of minus t multiply delta is equal 7 multiply delta. This means I can consider 12 minus 7 multiply delta, or if you don't like, you can consider 12 multiply exponential function, it doesn't matter what, multiply delta. In any case, 5 exponential function up to minus t, in this case, multiply delta. Why this doesn't, let me say, does not change, let me say, the result? Because this exponent here, this function, at time 0 is 1. And we have the effect of delta. Outside from 0 is delta that, let me, that's the difference. Look at this. 7th exponential of minus t multiplied delta. Let me represent in this form. It's clear. This arrow here is a little bit extremely abstract because I told you that this means infinite. This means 7 times infinite. For us, doesn't no particular meaning 7 times infinite with respect to infinite. Is in a form, let me say, of infinite, but 7 times infinite, because outside 0, delta put everything to 0. And at 0, this is 1. This means it's delta. This function here, exponential function, doesn't matter what. Minus t, plus t, it doesn't matter what the exponent. It's always a delta. 1 in this case, right? I don't know if this now clarify why, right? So, but if you don't like, you can write 5 exponential up to minus 1 delta. It's the same. Okay, now let me graph this expression. Let me graph here close to this, in which, let me again use the same notation, sigma. T I forgot, but anyway, it's intuitive. Okay, before closing the switch, we have again 5. Let me consider in a red, if I find quickly. Color. Because before 0, we don't have any delta. This means remain as we have. Again 5. But now, when I apply the delta, I have this expression here. This means, what happens in your opinion? We have the value. Then it's going to 0. Now I give you a little bit better. Let me see. What is this? Let me see. Very good. Yeah, probably. Yeah, I'm representing this form. Practically, we have an impulse from 5 to 7, and then going to 0. Let me see if I make some calculation mistakes, but I don't think so. Did you see something wrong?
The jump up to switch because of the signal.
Yeah, I mean, at time 0 minus, we have 5. Then we jump. Because of this,
Yeah.
before of the, I would like to say the delta in the sense. Because the input now is this delta here.
Yeah.
Let me see if I can improve a little bit the explanation. Let me see.
Oh. Perfect.
Let me see if I can use different words to explain. This, I would like to say, I would like to improve, Alex, I don't know if you agree. This impulse here, now graphically, it seems to be that is ready at 7, but really, if you read the expression here, what happens at time 0, this is 7, but here we have 5 times infinite. This means, to be exactly precise, practically it's something like that. But mathematically, we have something extremely abstract that is 5 times infinite that we would like to write. So, and then exactly at 0 plus, it's 7. It's clear, it's extremely abstract. Sometimes we find exactly what I told you, the file here, because what happens at exactly at 0 is not exactly a 0 plus. I mean, it's easier to understand if you look at the equation. At 0 plus, this is 0. And at 0 plus, it's 7. In fact, it's correct. What I can really represent is 7. Sometimes in some books we find an arrow until 7. But what happens at 0, not at 0 means at 0 plus, is 5 times infinite. And then I have to put an arrow theoretically infinite large. 5 times infinite. At the end, what happens at 0 is not possible to represent. Also, practically, if you measure in the measure, yeah, we say 7, because what happened at 0, it's, I mean, not concretely. If I apply a delta in the context of the mathematical delta, infinite amplitude, we will broken down everything, because we will have 5 times infinite. This means explosion of everything. We destroyed everything. What in really practically means, it's not exactly so, means what I told you at the beginning. What we can do practically, I would like to show you in a publication of us in which we use this concept or this technique in the control system. But what we apply practically, let me switch in order to, where is now, I'm totally confused here. Where is Zoom? Here. What we can do is just this. One of these 3, or we can also tend to an ideal delta, reducing this interval and considering the large amplitude. It could be that I have time to show you in Simulink what we did. This, in accordance of the maximal, let me say, input, which is the system can accept. But practically, we can do just this one. Never this. Therefore, mathematically, it's correct what I told you here. Theoretically, I have to consider 5 times infinite. Practically, at the end, we have something that at 0 plus, we will start from 7. But if really we apply the delta infinite, we've broken down everything. Mathematically, is everything correct? Okay. Next week, we have 2 blocks. I hope to go ahead with the Laplace. So we will reconsider this aspect here. It could be that I will improve also what I told you. Try to calculate the current here. Because the current is extremely difficult what happens. Because the derivative of delta, remember, is in a distribution, it's not a function. Of course, this is in the sense mathematically. Practically, again, is a little bit easier because why? Because basically, do you remember? I told you that practically we represent an impulse between 5 and 7. Because with an impulse between 5 and 7, not exactly an ideal impulse plus infinite. Now, the derivative of this function here, in which we spring not to infinite, but to 7, is possible because we have a 0 and an impulse. If you consider a function 5 until 0 minus, let me say at 0, not infinite, but 7, the derivative of this is 0, impulse, and then the exponent. Should I do? But if I have the delta, this is really extremely abstract because the derivative of the delta is in the distribution, it's not the function. Practically, basically, phenomenologically, and let me write this to conclude the lecture. What about, it's interesting, this is. The current. The current, I mean, you see delta, no? Now, you see delta of t equal c times, do you remember, the derivative of u c delta of t. In this sense, let me say so, in this context, we consider the practical solution, which is this here. Let me write the 5, and then it's going to 0, no? The practical solution of u c sigma, excuse me, sigma. The practical solution came from the practical delta, which is never infinite. This means you see sigma, sigma, it seems to be a delta, yeah, in our case. Means basically 7 exponential of minus t sigma. And the derivative of this which is the answer with respect to the input delta, is minus 7 exponential minus t sigma plus 7 exponential up to minus t multiply delta. Let me conclude rewriting everything. This means, again, you see delta of t equals -7 x. I am copying, in order to have in the one slide. But this, do you remember? This is 7 times delta of t. Graphically, you have something like that. Let me do with the red color. Oh, I lost. Yeah, with this. Really, I do this lecture in Zoom for the student. I'm happy to do, but sometimes for me to find together with to manage the Zoom and everything. Okay, the derivative is this one. This means starting 5 remain 5. No, it's 0, no, because it's open the circuit. We know because the derivative of 5 is 0. We don't need to clarify this, no? Because it's in a constant derivative. Anyway, or you can consider before closing the switch, we don't have current. And if you have to represent this, we have mathematically an impulse of 7 times delta, 7 times infinite. Then we spring to -7. Interpretation of this. Why it makes sense? Before closing the window. This is the situation. I have a better picture here. Before closing, we don't have current. Therefore, the derivative of 5 is 0. When I close, I have an impulse because the source, the voltage source is in the impulse. I have an impulse in this direction, and the current is this direction, positive. It's clear. But after that, here is the short circuit because delta becomes 0. This means the current, let me say, is in the other direction. It's clear, no? Invert immediately. But of course, this is in a practical aspect. If I consider the last sentence, the mathematical solution of 5 delta is a little bit different. It's mathematically extremely complex. But practically what we want to, at the end, is let me say, is complex just at time 0, because the derivative of delta is in a particular function and distribution, which I just sketched last time. But practically we have something like that. What happens at 0 is more complex than this one, but this is practically what happens. An impulse, infinite impulse 7 times. 7 also extremely abstract to think. What is the difference between infinite and 7 times infinite? Just the mathematical representation, but yes, quite clear. We have a charge immediately and then invert the current because we have a short circuit, no? At 0 plus. Okay, thank you. Next week we accelerate a little bit with the Laplace, and then after next week we will start with the dynamics in the context of control. Basically, the dynamics of a controlled system. We will look some basic control schemes with its dynamics in the control loop structure. We will reconsider again this example of aerostat system, car, in order to see what happens if I introduce a controller with its dynamics. Okay, thank you for your question. Ziri, excuse me. I will upload all material last time and this time in the folder of today with the lecture, which we reconsider. Thank you for your attention. I hope I try to summarize very quickly what we did last time. Last time we did 2 blocks. Anyway, look at the material, look at them on the YouTube. Thank you for the participation.